Welcome to today's lecture on scientific notation. I'm Drew Collop. In this lecture, we're going to take all the knowledge you've obtained using exponents and now apply it to scientific notation. Scientific notation is a way to represent very large or very small numbers. Using exponential notation, I'd like to express the following numbers in terms of base 10, meaning I want 10 to some exponent. Give that a try now. Let's take this up. We have 10. How do we express that? Just 10 to the 1. 100, 10 to the 2, and 1,000, 10 to the exponent 3. In terms of 1 over 10, remember what this is equal to. This is 1 over 10 to the 1, and then I can bring that up to the top, and this becomes 10 to the minus 1. Same thing with 1 over 100, 1 over 10 to the 2, bring that up to the top, 10 to the minus 2. Finally, 1 over 1,000, we bring that up to the top. And that's how you express those values in terms of base 10. What you can see here, the value of the exponent of the base 10 is the same as the number of zeros in the number. So here 1 0, exponent 1. 2 zeros, exponent 2. 3 zeros, exponent 3. Same with these ones here, 1, 2, and 3. If the number in question is greater than 1, we have a positive exponent. These are all positive. If your number is less than 1, 1/10th, 1/100th, 1/1000th, these are all negative exponents. Now that we've reviewed exponents, let's talk about scientific notation. Any number can be expressed in scientific notation using this form here. A times 10 to the exponent b. I've just put a and b as variables. A few things to note. A is written between 1 and 9.99999. It has to be a single digit in the ones column. There is no tens column, no hundreds column. It's only a single digit in the ones column. And everything else comes after the decimal. So it can be 1 all the way up to 9.99999, but it can't be 10. Remember that. B is the exponent on the base of 10, and this can be positive or negative. So if it's a positive number, we're going to make that number much larger. If it's a negative number, that number gets much smaller. As an example here, 9.0 times 10 to the 4. You can see this number here. It's 1 or greater, but it's less than 10. And here we have our exponent of 4. We can also have 1.25 times 10 to the minus 7. Again, this number is 1 or greater, but less than 10. And again, our exponent here can be positive or negative. Let's review the process of converting a standard number, the way that we usually express numbers, into scientific notation. So let's go through them. If you do not see a decimal, you assume the decimal is at the end of the number. We reviewed this when we were talking about percentages earlier in the course. Convert that number to a value 1 or greater, but less than 10, by moving the decimal point either left or right. You then multiply a base of 10 with an exponent equal to the number of spaces the decimal was moved. If you move the decimal and you made the number smaller, the exponent will be positive. If you move the decimal to make the number larger, the exponent will be negative. Let's now look at an example. This example says write 175 in scientific notation. So let's follow the steps. Step number 1. Find the decimal. There is no decimal, so we assume it's at the end of the number. Step number 2. Convert this number so it's 1 or greater, but less than 10. So I have to move the decimal place over 2 decimal places. This now gives me 1.75. 1.75 is a value 1 or greater, but less than 10. I then use step number 3, multiply this number by a base of 10 times 10. We move the decimal place over 2 spots. Therefore, our exponent on our base of 10 will be 2. Now, is this positive 2 or negative 2? We went from 175 and we converted it to 1.75. This was a big number and we converted it so it had to be a smaller number. Therefore, our exponent has to be a positive number. It has to offset that. Because this is small, this has to be big, so we don't change its value. Therefore, this exponent is positive. So in the end, you don't need the positive symbol there. 1.75 times 10 to the 2. That is 175 in standard notation, now written in scientific notation. Let's try another one. Write 0.175 in scientific notation. First of all, find the decimal. There it is. Convert this to a number between 1 and 10. Move the decimal over 1. So this gives me 1.75, again, times 10 now. We move the decimal place over one spot, so our exponent is going to be 1. We took 0.175, we converted that to 1.75. This was a small number. We convert it to a big number. So to offset that, this value has to be small. Therefore, our exponent on there will be negative. In the end here, 1.75 times 10 to the minus 1. Final answer. Here's some practice problems. Let's try the first one together. So we have 1,543,000. Let's convert this to scientific notation. We find the decimal. It's here. We move it 6 spaces over. This gives me 1.543. Now, we look at those zeros there. We will assume those are placeholders. They're not significant digits. So I just remove them from the number. I then multiply by 10. I move the decimal place over 6 spaces. 6 decimal places I moved it over. Therefore, our exponent is 6. We took a number larger than 1 million. We made it between 1 and 10. So we took a large number. We made it small. To offset that, we have to have a very large number as our exponential value. Therefore, our exponent here will be a positive value. That's it for question A. Try the next 3 on your own. Let's take them up. Move this over 3 decimal places. 1.543 times 10 to the 3, because we moved it 3 decimal places. We took a very small number. We made it very large. So to offset that, we have to have a very small number on our exponent. So minus 3. This value here, 3, 6, 9 decimal places. 5.821 times 10 to the 9. We took a very large number and made it small. To offset that, we have to make sure our exponent is very large. Lastly, now we have 3, 6, 9, 12. 2.46 times 10 to the 12. Is it going to be a positive or negative exponent? We took a very small number. We made it much larger. Therefore, to offset that, we must have a negative exponent on that base to make sure the value doesn't change. Think about this. If we had 2.46 times 10 to the positive 12, that would be a huge number. That's not what this number represents. This is 0.0000000000024, a very small number. Make sure you're aware of that. Also note, the zeros were placeholders. So these zeros here, these zeros here, these zeros here, and these zeros here were all zeros to indicate the proper place value of the numbers that were not zero. We assume they are not significant, so when we write it in scientific notation, they are removed. Don't forget that. Also remember, this A value, the number that comes before your base of 10, it must be 1 or greater, but it must be less than 10. Ask yourself that. That's the biggest mistake students make when they're doing scientific notation. They write the A value, that number that comes before the exponent, they write it as a value greater than 10. No, there should only be one number in front of the decimal. If there's more than one number, you've done it incorrectly. Let's build on that. Now we're going to look at how to convert a number that's multiplied by a base of 10 already. This could be a number you have, or perhaps you put it improperly in scientific notation. For instance, these all may appear to be in scientific notation, but they are not. Greater than 1, less than 1, less than 1. So let's explore how we're going to convert these into proper scientific notation. Step number 1, we're just going to completely ignore this part. Just temporarily imagine it's not there. Let's convert 247 over to proper scientific notation. We move the decimal place over 1, 2 spaces. This gives me 2.47 times 10 to the positive 2. Let's now put this back in, times 10 to the 8. So this value is here, and this value is here. What we now do is we work with those together. Remember, when we're multiplying or adding values together only, it doesn't matter which one comes first. So in this case here, let's combine 10 to the 2 and 10 to the 8. Remember how to do this using your exponent laws? We're multiplying them together, so we add them. 2 plus 8, giving me 2.47 times 10 to the exponent 10. Final answer. Let's try the next one now. Again, we're just going to forget about that temporarily. We're going to convert this number into proper scientific notation. Move this over 1, 2 decimal places. 8.7. Ask yourself, is this a number between 1 but less than 10? Yes, it is. We move the decimal place over 2 spaces, so my exponent is 2. We took a small number and made it bigger, so I have to make that minus 2. Let's now put this back in, times 10 to the 3. Combine those together first. 8.7 times 10. We're multiplying two exponents with the same base, so I add those together. Minus 2 plus 3 is 1. So the final answer is 8.7 times 10 to the 1. Last one now. Convert this to a number between 1 and 10. Move the decimal place over 1. 8.41 times 10. We moved it over 1, so exponent's going to be 1. We took a small number and made it bigger, so this has to be a negative number. Then we multiply by the second base raised to the exponent. Combine these together now, 8.41. We're multiplying them, so I add them together. Minus 1 plus minus 2 is minus 3. Final answer. Your turn now. Practice by writing all these values in scientific notation, A through J. Give these a try now. Let's take them up. First one, convert this over to scientific notation. 3, 6, 7. 3.8894675 times 10 to the 7. We're taking a very large number, we're making it smaller, therefore our exponent must be positive. Please note, write down all those numbers. Don't round it off. Sometimes when students convert a very large number over to scientific notation, they eliminate some of the numbers. Please don't do that. Keep all the numbers. Next one here, we move it again, 3, and we move it 6. 3.7794. These zeros here are placeholders. They are not significant. Therefore, we will not write them in to scientific notation. Multiply by a base of 10. We moved over 6 values. We took a large number, made it smaller. Therefore, it is a positive exponent. Next one, moving this over 3, 2.802. Again, is this number between 1 but less than 10? Yes, it is. Also note, these zeros were also placeholders, so I do not write them in the scientific notation. Multiply by, I move this over 3 decimal places. I made a small number bigger, so I have to offset that by making that a small number. Here I created a bigger number, so here I have to offset that by making this a small number. Let's try the next one now. 32 times 10 to the 4. Please note this is not in proper scientific notation. 32 is not a number between 1 and 10. 32, it's bigger than 10. So we must convert this over to proper scientific notation. Move the decimal place now over 1. 3.2 times 10 to the positive 1, because we made a big number smaller. And then multiply that, 10 to the 4. Combine these together. 3.2 times 10 to the 5. We're multiplying two values with the same base. Therefore, we add the exponents together. Next one now. move the decimal place over 1, 4.92 times 10, we moved it over 1. We took a big number and made it smaller, so that becomes a positive exponent, times 10 to the 7, 4.92 times 10 to the 8. Here, move the decimal place that direction 1, 3.87 times 10 to the minus 1 times 10 to the 4. Combine those together, 3.87 times 10 minus 1 plus 4 is positive 3. Now here we have a large number multiplied by a very small number. Let's work that one out. We move the decimal place 3, 6, 7 decimal places over. 6.72 times 10 to the positive 7. Notice these zeros here are only placeholders to tell us that the 2 is in the hundred thousands column. So when I write it in scientific notation, I am not required to write those zeros in. Multiply that by 10 to the minus 5. Now I combine those together. 6.72 times 10. Same basis, multiplying, so I add the exponents together. 7 plus minus 5 is just 2. Last three problems here. Move the decimal place over 1. 4.37 times 10 to the positive 1 times 10 to the minus 6. Combine those together. 4.37 times 10. 1 plus minus 6 is minus 5. Next one, move this over 3 decimal places. 8.41. Again, those zeros are only placeholders. Times 10. I move this over 3 decimal places. I made a small number bigger, so to offset that, I have to make this number negative, right? This is a bigger number, so I have to make this a small number. Times 10 to the minus 2. 8.41 times 10 minus 3 plus minus 2 is minus 5. Last one now. Move this over 2 decimal places. 1.25 times 10. Moved it over 2. Big number became smaller, so this remains positive. Multiply that by 10 to the 0. And here we add these together. 1.25 times 10. 2 plus 0 is just 2. So hopefully you didn't have a problem converting those over to scientific notation. Now we're going to look at the process of going the opposite direction. Before we had standard notation, and we were converting it to scientific notation. Now we're going to take scientific notation values and convert them back to standard notation. The first thing you want to do, you want to look at the exponent. If it's a positive exponent, we move the decimal right to make the number larger. If it's a negative exponent, we move the decimal to the left to make the number smaller. And we add zeros in as placeholders to indicate those numbers in the correct place value. So here we have 1.63 times 10 to the 3. This is a positive exponent. Therefore, this number is going to get larger. We're taking 1.63 and multiplying by 10 to the 3, which is the same as taking 1.63 and multiplying by 1,000. We multiply by 1,000, it gets 1,000 times larger. So we have to move this over 1, 2, 3 decimal places over. We put a 0 in as a placeholder, so in the end, this value is 1,630. This 0 here is a placeholder. It is not significant. It is there to indicate that this is in the tens, hundreds, and thousands column. Let's try the next one. 1.5 times 10 to the 4. So this number gets larger. I have to move the decimal place to the right. 1, 2, 3, 4. Put in zeros as placeholders, and I get 15,000. Please do not put a comma in there. We do not use commas in numbers in science. If you'd like to put something in between every third value, you can leave a little space in between. Let's look at these two now. I have 1.63 times 10 to the minus 3. So this is a very small number. Very small. 10 to the minus 3. 1/1000th. So this number 1.63 has to be 1/1000th smaller. So I take this and I move this over 1, 2, 3 values over, putting in zeros as placeholders. This gives me 0.00163. Again, please note, These zeros are placeholders. Also note, never write a decimal as the beginning of a number. There must always be a 0 if there's no other number in front of the decimal. Let's try the next one now. 1.5 times 10 to the minus 4. 1.5 times 10 to the minus 4. So this number is going to become a lot smaller. I move this over 4 decimal places. 1, 2, 3, 4. And I put in zeros as placeholders. And again, if there's no number in front of the decimal place, we always start it with 0 decimal. We have 3 zeros afterwards, 1, 5. So let's write that down. Note, must always have a 0 before the decimal. Don't forget that. Here's some practice problems now. Convert these numbers from scientific notation into standard notation. Now note some of these values are not in proper scientific notation, but hopefully you can still figure it out. Give these a try now. A through H. Let's take them up. 5.02 times 10 to the 5. This number is going to get a lot larger. So we move this over. 1, 2, 3, 4, 5. Fill in zeros as placeholders, giving me 5, 0, 2, 1, 2, 3 zeros afterwards. Next value here, 2.3498 times 10 to the minus 5. This number is going to get a lot smaller. Move this over 5 decimal places. 1, 2, 3, 4, 5. Put in zeros there. 0 decimal. 1, 2, 3, 4 zeros, then 2, 3, 4, 9, 8. Make sure you write all those numbers down. These numbers are important. These numbers are placeholders. So all those numbers are important, but only these values here are significant. 7492000 times 10 to the 4. This number is going to get larger. I find the decimal place and I move it over 1, 2, 3, 4 spaces over. 1, 2, 3, 4 zeros in place. This number was large. It gets even larger. 7492000. 0000. So there are 7 zeros there. Our next value, 7639 times 10 to the minus 3. This is a negative exponent, so I move this over to the left 3 spaces, making it smaller. 7.639. Next up, 0.3913 times 10 to the 6. So this number is going to get larger. 1, 2, 3, 4, 5, 6. This number becomes 391,300. This value here, very small number, very large number. 0.12345 zeros and then 64. I'm moving this decimal place over 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Make sure you count those zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So this value here becomes 64 followed by 1, 2, 3, 4, 5, 6, 7 zeros. 1, 2, 3, 4, 5, 6, 7 zeros. This value is 640 million. 0.0729 times 10 to the minus 4. You can move the decimal place over 4 digits to the left, make it even smaller. 1, 2, 3, 4. Put in zeros as placeholders, giving me 0.123455729. Lastly now, 23 times 10 to the minus 4. 23, 10 to the minus 4, it's going to make it a smaller number. 1, 2, 3, 4. This becomes 0.0023. So that's how you convert values from scientific notation into standard notation. Let's now examine performing mathematical operations with scientific notation. First, we'll discuss addition and subtraction, then multiplication and division. Addition and subtraction is actually much more challenging than multiplication or division. The reason why, if we're adding or subtracting two numbers, the exponent on the base must be the same. If they're not the same, we adjust them to make them equal. We then add the a value, the number that's multiplied by 10 to some exponent, and then we put them over the same power of 10. Let's go through the process and show you an example. Step number 1. You want to make sure that they have the same exponent on the base of 10. Step number 1 is already complete. For example 10, you can see they are both in terms of 10 to the exponent 4. Step number 2. Add or subtract the a values. So here's those a values there. 2.3, we are subtracting minus 1.2. And then we're going to multiply by the exact same base of 10 to the 4. Combine those together. 2.3 minus 1.2, 1.1 times 10 to the 4. This one was not so challenging because these were already the same. Let's examine the next one. We look at this one now, and we see they have a different exponent on the base of 10. Step number 1 is we convert both numbers so they have the exact same exponent on the base of 10. It doesn't matter here whether we convert them both to 10 to the 2 or convert them both to 10 to the 3, as long as they are the same. I'm going to convert them both to an exponent of 2. Here, we have 10 to the 3. I want to reduce that down 1 decimal place. Now, to compensate for that, because this one's going down, this one has to go up. Up 1 decimal place, meaning it has to get bigger. So I move the decimal place once to the right, giving me 50 times 10 to the 2 plus 3.0 times 10 to the 2. Now that I have them in terms of the exact same exponent, I now add those a values, no need for a calculator, 53, and then I multiply by 10 to the 2. Step 4 is convert to proper scientific notation. Please note, 53 times 10 to the 2 is not in proper scientific notation. Is 53 a value between 1 and 10 but less than 10? No, it's not. It's more than 10. To convert this to proper scientific notation, we move the decimal place over 1. This gives me 5.3 times 10. If I'm looking at just the 53 times 10, we took a big number and made it smaller. Therefore, this number has to be bigger. This value became small, so to compensate, this one has to stay big. We then times 10 to the 2. Let's combine those together. 5.3 times 10 to the exponent 3. Final answer. You can see when we have a different exponent on the base of 10, we must convert them first so they have the exact same exponent. We do that by adjusting that a value, that number that comes before our base of 10 exponent. Let's try the next one. You can see we have different exponents. We have 3 and we have minus 2. Let's put them both in terms of 10 to the 3. This one has to go up. How do I get from minus 2 to 3? I have to go up 5 decimal places. To compensate, this one has to go down 5 decimal places. So let's write that down. 7.0 times 10 to the 3 plus, in this case here, we're adding 3.0. We're going to convert it to 10 to the 3. You can see here, this one went up by 5. This one has to go down by 5, meaning the number has to get smaller. 1, 2, 3, 4, 5. Put in your zeros there. Let's clean it up on the next line. 7.0 times 10 to the 3 plus 0 decimal. We have 1, 2, 3, 4, 3, 0 times 10 to the 3. Now that we have them both in terms of exactly the same exponent on the base of 10, we can now combine those together. No need for a calculator. 7.12343 times 10 to the 3. Final answer. At this point in time, rounding would probably come into play. You can see that 3 times 10 to the minus 2 has almost no effect at all on this number. For now, we're not going to be rounding off until we talk about significant digits in the next lecture. We will assume these are all exact numbers. Exact numbers have an infinite number of significant digits. Let's try 13. 13 is a challenge. With the other ones, when they're different exponents on that base of 10, you can actually use your calculator and you can do it to sort of get around having to convert them over. But once those exponents get sufficiently large, either negative or positive, your calculator will no longer help you. So let's look at these. I have 10 to the minus 125 and 10 to the minus 127. Let's put them both in terms of minus 127. How do I do that now? Does this value have to go up or down to get to minus 127? Be careful. Minus 127 is smaller than minus 125. Remember that. So to bring this to minus 127, I have to bring this down 2 decimal places. To compensate, I got to bring this up 2 decimal places. So this will give me, if I want to move this 2 decimal places, 3.0, I move it 2 over, and I get 300. So this becomes 300 times 10 to the minus 127 minus 5.0 times 10 to the minus 127. Now I have them both in terms of the exact same exponent, minus 127. No need for a calculator. 300 minus 5, 295 times 10 to the minus 127. Not proper scientific notation. I move this over 2. Number gets smaller, so this other number has to get bigger. 2.95 times 10 to the minus 125. Final answer. Make sure you learn this. You can expect on your next assessment, you will get a problem just like this. Here we have 10 to the minus 4 and 10 to the 2. Let's put them both in terms of minus 4. To bring 2 into minus 4, I have to go down 6 decimal places. To compensate, this has to go up 6 decimal places. This will then give me 0.3 times 10 to the minus 4. Over here, I'm moving up 6 decimal places. That means the number's getting bigger. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. So this becomes 5 and then 6 zeros afterwards. Times 10 to the minus 4. Oh, don't forget your symbol. It's not multiplied, it's subtraction. We subtract that. No need for a calculator. We have 4,999,999.7 times 10 to the minus 4. Let's convert this back to proper scientific notation. 3, 6 over. This becomes 4.9999997 times 10 to the 6 times 10 to the minus 4. And then lastly here, 4.9999997 times 10. 6 minus 4 is 2. Final answer. Oh, I forgot one. I forgot something here. What did I forget? Forgot the negative sign. Always double check your work. It is negative. There we go. So once again, you can see that 0.3 times 10 to the minus 4 has almost no effect on the 5 times 10 to the 2. We will discuss this more later on when we get into significant digits. So that's adding and subtracting of numbers in scientific notation. Here's some practice problems. Try these now on your own, and I'll take some of them up. Let's take the first one up. So we have 10 to the 2 and 10 to the minus 1. Let's put them both in terms of minus 1. So this one has to go down 3. This one has to go up 3. Let's move this up 3. 1, 2, 3. Number's getting bigger. 6,010. 6,010 times 10 to the minus 1 plus 5.3 times 10 to the minus 1. Combine those together. Hopefully you don't need a calculator for this. adding those together. We're going to put this in proper scientific notation. I move this back. 1, 2, 3. The number is getting smaller, therefore my exponent's getting bigger. So that's going to be 3 decimal places, 10 to the 3. 3 plus minus 1 is 2. 6.0153 times 10 to the exponent 2. Final answer. B, not very difficult. I'll just write the answer for you so you can double check. C, also I don't think is very difficult. Just don't forget the negative sign. Let's take up D. We have 10 to the minus 95 and 10 to the minus 90. Let's put them both in terms of minus 95. So 10 to the minus 90, if I want to make it minus 95, I have to go down by 5. To compensate, this has to go up by 5. 2.1 going up, meaning it's getting larger. 1, 2, 3, 4, 5. 1, 2, 3, 4 zeros in there. This now gives me 9.3 times 10 to the minus 95 plus 210,000 times 10 to the minus 95. Combine those together. Again, hopefully you don't need a calculator. Times 10 to the minus 95. Not proper scientific notation. 1, 2, 3, 4, 5. We make that number smaller. That means this number gets bigger over here. 2.100093 times 10 to the minus 90. Final answer. So adding and subtracting numbers in scientific notation can be a challenge. Multiplying and dividing, I think, is much simpler. Let's go through the process now. So we multiply or divide numbers in scientific notation. We multiply or divide those A parts, the decimal parts, and then we multiply or divide the powers of 10 separately. So let's go through the process, and we'll go through example 15 together. Step number 1, multiply or divide those A values. Here's those A values. We're dividing. This is 6 divided by 3. We are then going to look at our exponents here. We are then going to apply our division to those. So that's step number 2. Step number 3 is we multiply those two together. There's no need to put the multiplication symbol in. If I remove it, the brackets mean the same thing. I then do the operations here. 6 divided by 3 is 2. We have 2 exponents. We're dividing them, so I subtract those values. 10 to the 3 divided by 10 to the 2. I subtract them. 3 minus 2 is 1. 2 times 10 to the exponent 1. If it was not in proper scientific notation, you would have to convert it over to proper scientific notation. Let's try some more practice problems here. So here we have 9 and 2, and we're multiplying. So 9.0 times 2.0, and then we're doing 10 to the 7 times 10 to the minus 2. Again, please note, we are multiplying these together, therefore we multiply those together. Over here we were dividing, so that's why we divided those values. Let's do the math now. 9 times 2 is 18. 10 to the 7 times 10 to the minus 2. I'm adding them. 7 plus minus 2 is going to be 10 to the 5. This number is not in proper scientific notation. I move the decimal place over 1, giving me 1.8. I made a big number smaller, so therefore I have to increase my exponent by 1. Final answer. Let's do example 17 now. You can see we have those two values and we're dividing them. 2.4 divided by 1.2, and then 10 to the exponent 4 divided by 10 to the exponent 4. Now notice here we have the exact same exponent here on our base of 10. However, when we're multiplying and dividing, it doesn't matter. Let's do the math now. 2.4 divided by 1.2. Notice I picked some nice easy numbers. That's exactly 2. We have 10 to the 4 divided by 10 to the 4. So I'm subtracting it. 4 minus 4 is 0. 10 to the 0. That's the same as saying 10 to the 1, which is the same as saying 2. Lastly now, again, it doesn't matter that these are different because we are multiplying them. So we do them separately. 0.03 times 5.0 Multiply this, 10 to the minus 4 times 10 to the positive 2. Combine those together. Here we get 0.15 times, we're multiplying them, so we add them. Minus 4 plus 2 is minus 2. Here, this is not in proper scientific notation. This number is less than 1. I have to move the decimal place over 1, making it bigger. Therefore, our exponent gets smaller. 1.5 times 10 to the minus 3. Final answer. So that's the process of multiplying and dividing fractions. I think this process is easier than adding and subtracting. Let's finish up by trying some practice problems. A, B, C, and D. Give those a try on your own now. There's the answers to those problems. Let's take a few of them up. Let's take up the first one. So here we are dividing two numbers in scientific notation. So let's separate them. 8.24 divided by 4.12. Multiply that by 10 to the 3 divided by 10 to the minus 12. So don't forget, we're dividing those values. Divide those. Notice I picked a nice easy number there. Divide those. 10 to the 3 divided by 10 to the minus 12. That's 3 minus minus 12. Two negatives make a positive, so we're adding 12. So that's 10 to the 15. Final answer. B, I won't take that one up. C and D, let's take up C. So we're dividing it again. Combine those numbers. 6.1289, divide that by 3. Multiply that by 10 to the minus 4, divided by 10 to the 12. Remember, we're dividing, so I separate it and divide them like that. Notice this value is not a nice easy number like before. 2.0429666666 keeps going. Times 10, here we're dividing it. Minus 4 minus 12. Minus 16. Now notice this number's in proper scientific notation, but you can see we have a repeat here. So let's write that down as 2.04296 repeating times 10 to the minus 16. In the future, we would round this off. We haven't covered that yet. That's the topic of next lecture. And D, there's the final answer there. If you have any questions about that, you can contact me outside of class or during tutorial. So today, we took all the knowledge we learned about exponents, the exponent laws, and then we added on to that with scientific notation. Scientific notation is extremely important for your work in the lab, as you may be working with very large numbers, dealing with moles, or dealing with very small numbers. That's all for today. Until next time.